Hi everyone. So today I'll shortly post the second lecture video of the week, and then of course I'll then post the attendance quiz for the week, just to make sure that you've watched the both the lecture videos for the week, and then once you complete the attendance quiz for the week, you'll be listed as present. So today, the topic that I'm going to cover is the composition and structure of the atmosphere. Just before we start zooming in the atmosphere, just want to mention that the atmosphere doesn't exist alone, right? And there are different spheres within the planet system. We have the atmosphere, which is like the gases and solid particles alike. We have in the atmosphere, that is that's what's surrounding the Earth's surface. But most importantly, we also have other spheres directly contributing to the atmosphere, right? Such as the hydrosphere, which refers to all the water bodies that we have on Earth, and this also include what we call the cryosphere, which is like the ice on the planet, right? So it's a very, very important source of fresh water that's stored in the ice sheets we have in both hemispheres. And then we have the lithosphere, which represents the solid Earth, which is the crust, mantle, and core. And then finally we have the biosphere, which is life on Earth. So why I'm showing you this is that without this, the other different spheres, the atmosphere, of course, would be fundamentally different, right? It's even hard to imagine the atmosphere without the different spheres, right? Whether we're talking about the greenhouse gases or the other particle forms, aerosols, they are sourced from either from the hydrosphere, the lithosphere, or the biosphere, right? So there is a constant interaction between all these spheres at all times. So just to help you visualize, like for instance, there is a constant engagement between the biosphere, which represents the plants and animal life on Earth, right? And with the atmosphere, so the biosphere also is dependent on the atmosphere, right? So the composition of the atmosphere is critical to sustain life on Earth. Without the atmosphere, there will be no life on Earth, to briefly to put it in short. So the hydrosphere is also very important. So because it's an important source for the atmosphere. So water, for instance, when you look at water vapor, right, and then the different rainfall formation processes we have in the atmosphere that are important to sustain life on Earth. And then, of course, we've briefly mentioned the feedback, how it is very important for both weather and climate processes, but it's also very relevant for the different spheres we have on this planet. So there is a constant exchange of matter between the different spheres, right? Like I mentioned briefly last lecture, there is the positive feedback mechanism, and then there's also the negative feedback mechanism. What I mean by positive feedback mechanism or positive feedback loop is when we have a case where the original a signal ends up being amplified, right? So for instance, if you cause a certain type of warming, and then for instance, if the warming causes an ice to melt, and that fundamentally changes the albedo effect of the surfaces that we come to know in the high latitudes, right? And then there is more insolation, and more heat is being absorbed by the new surface, and then that would amplify the initial warming condition, right? But unfortunately, when we're talking about this feedback loops, we have it's more of when we're talking about the the climate crisis, we have more of positive feedback loops rather than negative feedback loops. But we indeed have cases, we have examples of negative feedback loops, right? But these processes take much, they occur on a very longer time scales than it is the case for positive feedback loops, right? So what we mean by negative feedback loops is that, for instance, if we have initial warming and for some reason the system actually ends up dumping and then reducing the initial signal to cause a relative cooling at the end, then in those conditions we have what we call negative feedback loops. I will give you one example. For instance, when we have increased warming, and that would lead to increased weathering, right? And then more and more material will end up being buried in the deeper ocean. So that means it serves as a form of a natural form of carbon sequestration, right? And then in that case, we have what we call a negative feedback loop, right? Let's look at the carbon cycle as an example. Right? When we think about the carbon cycle, we're talking about the constant exchange between the different spheres, right? Remember, the atmosphere doesn't really exist on its own, right? It actually interacts with all the different spheres we have, right? As you can see here in this image, so there is the CO2, the carbon being released and also being stored by the ocean. So the ocean serves as both a source, can also can serve as an important carbon sink, right? And there is obvious burning of fossil fuels, of course. These are carbon sources from the biosphere, and then we also have carbon sources from the lithosphere in terms of, for instance, increased volcanic activity, right? And so we have, for instance, whenever this weathered material, right? There's a lot of soil, a lot of carbon in the soils, right? In the lithosphere, and then when the lithosphere ends up being stored somehow, finds its way to the deeper ocean, then it's actually can be considered as one example of the negative feedback loop, where we have simply put a potential source of carbon is being stored far away from the surface of the Earth, where we have always constant interactions between the different spheres. So there are important concepts that I would like you to know. For instance, the thickness of the atmosphere. So the thickness matter, right? Whether how thick or thin the atmosphere is on purpose. It's by design, right? So, but it's actually very difficult to establish or to put an upper boundary to the atmosphere, right? For instance, if you ask me, just like if we're just the portion of the atmosphere that's fundamental to sustaining life on Earth, it's actually, we could say, we can put the upper limit out to 100 kilometers, right? So that's where we have about almost 99.9% of the atmosphere is contained within the first 100 kilometers. But broadly speaking, it's really actually hard to put a limit to the atmosphere, right? But most importantly, the composition of the atmosphere, if we look at the composition of the atmosphere, of course, all these gases, like almost all of them, we have them in what we call, in the zone we call homosphere. I will come to that point later, where it's within the first 100 kilometers or so of from the Earth's surface. So what we see here more or less represents more or less represent all the gases we find in the what we consider to be an integral part of the atmosphere, right? And there are very, very important gases, and then so today I'll just give you this very important greenhouse gases we have in the atmosphere, right? So water vapor is a very, very important greenhouse gas. What I mean by greenhouse gas is these gases with the capacity to store to trap heat, right? So the greenhouse effect I briefly discussed in the previous lectures is like that's it's a very important concept within the climate and climate system, where it's these gases when present in naturally sorry about that. Fortunately, I'm recording today's lecture from my lab, so occasionally we have this the light might go off. So just to tell you why the greenhouse effect is very important is just maintain a constant temperature, right? It actually makes sure that the planet is has a reasonable temperature to sustain life, right? Without this greenhouse gases, it would be very cold. The atmosphere would be very cold, so it would be very difficult to sustain life on Earth. So we need these greenhouse gases, but as I'll talk in the next slide, I'll show you in the next slide. But there are different important greenhouse gases, but we need to especially when it comes to carbon dioxide, I'll show you why we need to be careful, right? And then control and reduce our emissions. But what we call these greenhouse gases, they are very efficient at trapping heat. And so water vapor, it's sourced from the Earth's surface, of course, from the hydrosphere. It's an extremely important gas because it's a source of moisture for cloud formation. But also, it's the reason why you find the summer to be unbearably very wide. Our summers here, especially if we're now very far away from the ocean, why the summer feels like it is 120 degree Fahrenheit, because it's just this water vapor is a very, very very efficient and has a strong capacity to trap heat. And the other one, and the most important one, is carbon dioxide, right? Carbon dioxide, even if it makes a very little of the atmosphere, and it's a very, very important greenhouse gas, because unlike water vapor, it has a long residence time, right? So it's very, very difficult to remove from the atmosphere, and so that means its impact on the global warming is much, much more pronounced, right? While when we're talking about water vapor, it's easily removed from the atmosphere, so we'd see this change on a daily basis, right? But for carbon dioxide, it's completely different. It stays in the atmosphere for a long period of time, and so it has its impact on the climate is actually major. And so here is a very important figure I want you to just look at. So I'm showing you the carbon dioxide change global carbon dioxide concentration, for the last 800,000 years, right? So this is nature, but what we have today here is, well, this is actually 2017. So the figure now is we have about 420 ppm of carbon dioxide in the atmosphere. So if you look at what was happening throughout history, so the change, so relatively the carbon dioxide in the atmosphere we were fluctuating between 180 to about 300 ppm at most, right? And then it was taking for nature, for our planet, to go from one peak to the other. For instance, for the carbon dioxide concentration to change by 100 ppm, it would take the Earth about 100,000 years, right? But what we have done within 115 years is we have done what used to take the planet 100,000 of years. We're doing it, and within a very, very short period of time. So the rate of change is actually nothing like we have ever seen in the past. So it's completely, that's actually one of the reasons that one of the scary aspects of climate change is the rate of change, right? And so since the 1950s, we actually were increasing, the concentration of carbon dioxide is increasing by about roughly about 1.8 ppm. This is like we have never seen anything like this. And then why it is why we usually focus put more emphasis on carbon dioxide. It's because it's very difficult to remove, and the atmospheric residence time stays in the atmosphere for a long period of time, so its impact is much more pronounced compared to other greenhouse gases like ozone or methane. So let me just briefly discuss what good ozone and bad ozone is, right? So you probably have heard of the destruction of the ozone layer, right? So ozone is a very, very important molecule in the atmosphere. So the good ozone, the ozone we have in the stratosphere, actually protects us from being exposed to UV radiation, right? UV radiation, as you all know, and that's why we have the UV index, because it's a precursor. It's known to cause skin cancers among other less understood health conditions. So the ozone, it could also be good, because if we have it in the stratosphere, far away from well, relatively speaking, far away from the biosphere, then it's really good, because it prevents the life on Earth, the biosphere, from harmful UV radiation. But we also have what we call bad ozone. These are ozone not directly released from the industries, but results in as a byproduct of this toxic chemical reactions we have in the troposphere. So it's when we have ozone formation in the troposphere, it is actually a harmful pollutant, and can trigger different health problems. But what you need to know is ozone is also a very efficient greenhouse gas. It's actually very efficient at trapping the UV radiation in particular, right? But the carbon dioxide, the other as a very, very potent greenhouse gas is methane. As you can see, it has actually not a very short residence time, right? Its atmospheric lifetime is between 10 to 15 years. So its impact can be whatever we are emitting today. Of course, it has compared to carbon dioxide, its impact would be felt on a shorter time frame, but it's still a very, very potent greenhouse gas, right? And then the primary source of methane is also agriculture is a primary source, but as you probably recall from the Chasing Ice documentary, that like we have a lot of methane stored in the soil, right? In the high latitudes, right? So if all the ice is, if the ice melts, like, and then this methane will be exposed, right? Once it is exposed, and then there will be a lot of methane emissions to the atmosphere that would cause significant warming in a shorter time frame compared to carbon dioxide, right? That's also a good example of a positive feedback loop, right? Okay, so what are aerosols? Aerosols are also important, but these are not necessarily greenhouse gases, right? These are actually small solid particles suspended in the atmosphere. They could be solid particles or liquid particles as well. And well, these are like usually there's the arbitrary scale. So typically we refer as an what we refer as an aerosol has so it is a specific diameter. So we're looking at 1/1,000,000th of a meter, right? And well, if it is big enough, it won't be suspended in the atmosphere anyway. So it can have both human and natural causes, right? So for instance, we can have Sahara Desert, right? Sahara Desert is a very important source of aerosol, which also surprisingly sustains life on the planet, right? In a way, sustains life, those microorganisms in the oceans we have. They actually this dust particles, right? At first they would actually that would end up in the atmosphere as an aerosol. Is also, once it is removed, it's also a very important source of nutrients for different organisms in the ocean, because the Sahara Desert used to be actually completely different, right? And then the sand is actually very nutrient rich, and then it actually helps to sustain life in this planet in a very complex way. And of course, when we have, for instance, volcanic eruptions, or typically we have we have these aerosols, and then on a shorter time basis, they actually impact. It can impact temperatures, right? So if we have aerosols in the atmosphere, what happens is that they interact with albeit on a shorter time basis, they interact with the Earth's energy balance, right? They are very good at reflecting back the incoming solar radiation. So while they are easily removed and then they have a short residence time, so they actually have a cooling effect on the climate. Okay, now like I said, it's very difficult to put an upper boundary to the atmosphere. So to say, the atmosphere has no distinct upper boundary. But when we look at there are very important divisions within the atmosphere, right? So here is a very important figure here. So if you look at the temperature change, typically, this is a typical profile that we see. It's common to everywhere, right? But what we see here is, for instance, in the troposphere, we have a constant decrease of temperature. As you can see here, constant decrease of temperature up to a certain point, right? While in the stratosphere, we have the temperature in a state of decreasing with distance, and it actually increases as we go up, as we go higher and higher. One of the reasons, the main reason, is that you all know this. What we have in the atmosphere, it's where we have the ozone layer. So why is the ozone important? Because it absorbs, it traps the heat, the UV radiation, the heat that comes in the form of UV radiation, and it ends up warming the surroundings. So relatively speaking, the temperature actually doesn't really cool that doesn't really cool as we go higher and higher in the stratosphere because of the ozone layer. And then in the mesosphere and in the thermosphere, we have in the mesosphere we have we're back to the condition where we see temperatures very abruptly decreasing with height, and then we have what we call the thermosphere, where in the atmosphere where we have more exposure to those very, very harmful gamma radiations as well. So, relatively speaking, we could consider even in the thermosphere the temperature actually increases, relatively increases with height, right? But it's very, very difficult to put a distinct upper boundary to the atmosphere, right? But this is very important, especially what's happening to the temperature in the troposphere and the stratosphere, right? Why is the case? Remember, it's because of the ozone layer interacting with the UV radiation, right? And so I briefly discussed this in previous lecture. So the solar radiation, we have the solar radiation comes in different energy forms, right? We have the gamma rays, the X-rays, and the UV rays, right? Thankfully, because of the atmosphere, so the atmosphere knows how to protect the biosphere from this harmful radiations, particularly the ozone layer, right? But we also have in the thermosphere where we have the interaction between this very short wave energy and with the particles we have in the thermosphere. So, but if we're looking at looking at the composition of the atmosphere, right? So what we have over the first 50 miles or so of the atmosphere, we have a very a continuous reaction and continuous exchange between the different gases we have, right? So we can consider what we call the homosphere, the first 50 miles of the atmosphere, or the first 80 kilometers of the atmosphere. We have more or less, we can consider it a well-composed part of the atmosphere, right? If we're looking at temperature, again, we can divide the atmosphere into 4 parts, right? If we're looking at the composition, we can actually only divide the atmosphere into 2. We have the homosphere, where we pretty much have all the gases, it's well mixed, and then we have the heterosphere, where we have the hydrogen, helium, and the oxygen, nitrogen, but like we don't really have these reactions, right? These chemical reactions between the elements we have, mostly because if we're looking at the noble gases like helium, of course, these are noble gases, they don't really react. Instead, the only reaction we have is like with the short wave, the only interaction these gases have is with the short wave radiation that comes from the sun. All right. So most importantly, remember, we have that most important molecule in the homosphere known as the ozone, between 20 to 50 kilometers, or within between I would say 10 to 30 miles, right? So just to show you how the ozone is important, here is a figure, a comparison between 1980 and 2015, right? I told you in previous lecture that how the chlorofluorocarbons are very important, and how ozone layer is very important because it protects us from the UV radiation, from the biosphere, like including humans, from being exposed to those harmful UV radiations, right? So the CFCs actually, as I'll show you in the next slide, they actually are since the 80s, we know that they can they can actually they destroy this ozone by reacting with the ozone molecule from the bottom up, right? We want the ozone layer to interact with the UV radiation. That's the primary purpose of having the ozone layer in the stratosphere, right? But because in the 80s we used to have these refrigerators that are where there were these refrigerators industries as well, emitting what we call the chlorofluorocarbons, the CFCs, and then the CFCs, as a result of complex physics, they find their way to the stratosphere, and then they end up breaking the ozone layer, right? So there is not, we don't really have enough ozone. We are still recovering, right? Enough ozone to protect us in some places, to protect us from the harmful UV radiation. So this is a very, very important crisis. But we have actually, after the Kyoto Protocol, there is an agreement to control the emission of CFCs, and we've made great strides in that effort. So if we look at, sorry about that again, I have to turn on the light again. All right. So if you look at atmospheric pressure instead of temperature, right? We see when we look at temperature change within the atmosphere, we see it's not linear. It doesn't simply decrease with height, right? As we go up. So what we see here, the typical trend is, as we go up, the atmospheric pressure decreases with height, simply because the atmospheric pressure is the weight of the air above it, right? So as we climb up, right, as we hike, that's why the air gets thinner and thinner. Of course, then the atmospheric pressure decreases as a result, right? So if I ask you, why does the atmospheric pressure decrease with an increase in altitude? The answer would be, as altitude increases, the weight of the gases above you decreases, right? These are the sort of questions I'll have in the exam, right? Back to temperature again, right? We see that, like, temperature has like different trends, right? At first, the first 10 kilometers or so, and then it consistently decreases with height, and then we have what we call the tropopoles, where that's the zone where the temperature neither increases or neither decreases. So it's the transitional zone. Then we have the stratosphere. Then in the stratosphere, where we have where we have maximum ozone concentration, what we have is a constant, more or less constant, relative increase in temperatures. And so if I ask you, why is the stratosphere relatively warm, the only reason is because it absorbs a lot of the UV radiation that comes from the sun, right? So that would be it for today. Again, there will be two or three questions, and for the attendance quiz for that will be posted today, and so we'll only cover the last two lectures, right? More or less the last two chapters that we have covered. One of them is on Monday. It was about the Earth's energy budget and seasons, and now about the composition of the atmosphere, the structure and composition of the atmosphere. So next Monday, and we'll talk about the atmospheric and oceanic circulations, and basically because this is divided into two lecture videos. So both Monday and Wednesday we'll look at first atmospheric circulations, then on Wednesday more about ocean circulations, right? Take care, guys.